The next process we're going to be talking about is transcription. And transcription is simply the process where you take your original DNA and you're going to be making a messenger RNA from this particular sequence of DNA. So I'm going to put a random piece of DNA down, and it's going to be TAC GCC GTA and ACT. Now, if we were looking at the DNA strand, again, we would always do the same thing we did with replication. We would separate the strands. When you're going to be making a transcription, when you're going to be making the messenger RNA, what you have to do, again, is here's your other strand, your ATG, and so on. Okay. The first thing you do is separate the strands again. But what's important when you do this is that only one side is going to be transcribed. The other side, nothing's happening with that one. It's never transcribed. It doesn't matter if it's an E. coli or an elephant or a human. You never transcribe the right-hand side. It's always the left-hand strand. So we're separating the strands. I'm going to recopy this over here. So TAC, GCC, GTA, and ACT. So now what we're going to be doing is making the messenger RNA. So what happens when you make a messenger RNA, some rules that are a little bit different. We mentioned that in DNA, A always goes with T, T with A, C with G, and G with C. However, with RNA, the A always goes with U because there's no thymine in RNA. You use uracil in its place. T goes with A, C goes with G, and G goes with C. So these are the same sequences, but this one is different. U is uracil. And so it's going to be substituted for any place that you would put in a T. So let's make the messenger RNA now. So in this case, T is going to go with A is going to go with U, C is going to go with G, and then you have your C, G, G, C, A, U, U, G, A. So this now is your messenger RNA. What happened to the other strand? It is simply sitting out here, ATG, blah, 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 blah. Okay, so the rest of this, all it does is it sits and it waits. This strand is never transcribed. It sits and waits, and as soon as the messenger RNA, which will come off, it will peel itself off of this, go out of the nucleus to the cytoplasm to find a ribosome. And so what's going to happen at ribosome, the ribosome is where you're going to be doing the next process, which is translation. So as soon as this messenger RNA peels off out of the nucleus to the cytoplasm to the ribosome, the two strands come back together again. So then you have your TAC and so on, and you have your original strand, your waiting strand, come back together, ATG. And so that's the completion. So then you have your double helix reinstated after transcription has occurred. Now it's important to note about transcription as well that not the whole chromosome is transcribed, only a piece at a time. So say you have a gene, we're looking at this TAC section we're looking at here, and this part is waiting. Maybe only this part is transcribed. The rest of the chromosome stays together. So visually, if you look at these, you'll see a bulge in a chromosome. This part is being transcribed. This part stays intact. This part stays intact. Then you'll have another transcription zone here where it's transcribed. This part stays intact, and so on. So it's only the genes that you're working on. Perhaps this is gene A, perhaps this is gene B, and then maybe there's another one down here that's gene C that is going to be transcribed to make a particular kind of a protein. The entire DNA molecule does not separate, only the little pieces that you need to make the specific, that code for the specific proteins that you have. The next step will be translation.